Okay folks, welcome to the tutorial for the Trace GC Voyager mass spec instrument. So this is a combination of a gas chromatograph coupled with a mass spectrometer as a detector. We also have an autosampler unit and a control box here for the autosampler itself. So when you get right down to it, there are three parts to the instrument. We have the autosampler, which handles the injection of a sample into the gas chromatograph. We have the gas chromatograph, which thermostats an open-bore microtubular column, such as this, where separation of complex mixtures in the gaseous phase will occur. And then finally, the mass spectrometer portion, which acts as the detector for the gas chromatograph. Now, inside of the mass spectrometer, we have an ion source, which actually ionizes and fragments species as they come off the column. And then those ions that we form, or ion fragments, will pass down through the quadrupole mass analyzer and ultimately to an ion detector where they are detected. Okay, so in this experiment, what we want to do is to determine the presence of volatile components found in various inks, which can be done for forensic analysis. So we want to go over an overview of how to use the instrument here. So the first thing one would do, and this may actually be enacted when you come in, is to double click on the Trace MS plus Tune icon. I've already done that, and if you do double click on that, what you're going to find is this little ball down here in the right bottom corner. I am going to right click on that, which brings up what we call the manual tune page. So we want to start by doing an air and water test to check for leaks in the system. So we're going to go to the manual tune page here, and this is what we see. Now within the manual tune page, we're going to see places for various peaks to come up. Now, what we're going to be doing here is looking for the helium carrier gas, which we'll come back and mention in just a moment. The helium carrier gas will occur at 4 AMUs, so essentially what I'm doing is I am ionizing a helium atom here by knocking an electron out of it to make a helium ion. So we still have 2 protons and 2 neutrons for a mass of 4 AMUs. Out here at about 18 AMUs, I'm going to be looking for ionized water molecule. Out here at about, in this region, I'm going to be looking for ionized nitrogen. That should be at about 28 AMUs. And then out here around 32 AMUs, I'm going to be looking for ionized oxygen molecule, or O2. Now, one thing to check before we get started is to be certain that we have sufficient carrier gas, which in this case is helium, moving through the column at all times. So I'll come to the helium tank, and I'll check the primary gauge here, which shows about 800 psi, which is sufficient. The secondary gauge is showing about 50 psi, which is also sufficient for our experiment. Just something worth double checking before we start. Now at this point, I'm looking here to the right at my readbacks here. Now, we can toggle between this screen and this screen by hitting the gray bar here, and you may find that when you enter into the software, you may not see the readbacks. So if you need to look at the readbacks, just left click on the gray bar and you can open up that menu. Now, these are various readbacks that we're getting, for example, that correspond to either temperatures or voltages applied to the mass analyzer itself, so that it can be an optimal operation. Now, what we would like to do, and I'll just double check here my temperatures, we have a source temperature, which is the ion source, setting at about 220 degrees Celsius, which is sufficient. The interface temperature, which is the interface moving between the chromatographic column and the ion source, is at about 250. And then we also have some voltages and such down here that correspond to the optimal operation of the quadrupole mass analyzer, which you will be telling me about in a post-lab question. So what we would like to do is to apply voltage to the ion source itself. Now the ion source is nothing more than a hot wire with voltage applied to it, and that is an electron source. So the electron comes off of the hot wire and it's accelerated toward an anode. And impact of that electron against material coming out of the column is what causes ionization and fragmentation to occur. So we want to hit the operate button here. So we're going to do a left mouse click here to turn the ion source on at this point. So the electron gun is happening, and we're going to look across here to our readouts. So what we're seeing here, and I'll just make this a little bigger so we can really focus in on it, is that we have a very large helium peak here. So what we're looking at is the total ion count on the y-axis as a function of AMUs on the x-axis, or masses. So notice that the helium peak is very large compared to the water, the nitrogen, and the oxygen. Generally speaking, we'd like the helium peak to be 95% or greater of the whole. We'd like to see the water and the nitrogen and the oxygen at less than 5% of the helium. If that's true, then we know we have a reasonably tight system. We don't have any air or water leaks. And again, we cannot compromise the vacuum because otherwise we will not get an accurate mass spectrum. So notice now that in terms of counts, the helium counts are sitting at about 10 to the 8th. Water counts are at about 10 to the 5th, so that's going to be almost 1 part in 1,000. We're also looking at about 1 part in 1,000 here and about 1 part in 10,000 here. So we're in really good shape here in terms of our air and water test. We have a nice, nice tight system here. No air or water to speak of is getting in. So I'm going to go back to my gray bar here, and I'm going to go ahead and turn the source off. Again, a left mouse click will do that, and we'll see these go away. All right, so at this point, I'm going to minimize the tune page. And now we need to move into the primary acquisition software, which is our Excalibur here. So we're going to go and double click on the Excalibur icon to bring up the main program. Now what you're going to notice here is that we have several windows that we can look at. This guy up here is what I like to consider as home base. So it takes me to all of my various options here in terms of setup, sequence, and browsing for analysis. So we can always come back to the home base here as needed. The other thing is we have the status box here. So the status box is telling us about the status of each one of our components. So you can see here that we're seeing the status of the autosampler, the status of the GC, and the status of the mass spec here. And what we see here is that these are awaiting instructions from the software once we look at an instrument setup. So let's next go to the instrument setup menu. Okay? Now, the first thing I want to do is I want to pull up the appropriate file that we're going to use. Since we're doing an ink analysis, I'm going to go and open the appropriate one, and I'm going to use the new ink file here. Okay, there it is, so we'll open it, and that should be the default file I already had in here. And what we can do is we can look at the default parameters for the autosampler, for the trace GC, and for the mass spec. So we'll start by looking at the autosampler here. So we have pre and post injection events as well as injection events. So this is where we control, for example, the sample volume that we're going to inject. So in this case, we're going to make a 3 microliter injection of our sample. We're going to be setting an injection speed here, and that's variable as well. Here's a pull-up speed, which is how quickly we actually draw the liquid into the syringe. How many sample cleans we want to do. So normally we want to clean the syringe before we use it. And then in terms of pull-ups, and we'll come back and see this as we actually see the autosampler work. We'll have 2 pull-ups of sample, 2 microliters per pull-up with a delay of 2 seconds after the pull-ups. Pre and post events, and again you can come back and double check this. We're going to do 1 pre-injection rinse, we're going to do 1 post-injection rinse. Each rinse will be at a volume of 3 microliters. Alright, so that takes care of the autosampler. Let's now move to the trace GC. So what we see here is that we are going to be programming the oven to remain isothermal at 120 degrees Celsius. So we found that we don't actually have to apply a ramp in this case like we would in some analyses, because the 2 components of the ink that we're looking at can be resolved at a constant temperature. And that's nice because if we're making lots of subsequent runs, we don't have to wait for the oven to be thermostated back to an initial temperature. The This is actually looking at the injector. We're actually going to be injecting at a temperature of 250 degrees Celsius, and the split flow is at 20 mils per minute. So what we're applying here is a split ratio of 10, which means that we're actually not going to be injecting all of the material that we apply in the injector to the column. And the reason for that is because of the sensitivity of the mass spectral detector. Let's go down to the mass spec. And what we have here is a defined mass range. So the mass spec will be scanning between 50 and 200 AMUs per scan. And we're going to be actually looking at a time range of the entire run of 0 to 5 minutes. Now, one thing you're going to notice here is that we're not actually going to start data acquisition until 1.5 minutes into the run. And the reason for that is we want to introduce what's called a solvent delay. And what that does for us is it allows all of the solvent to pass through the column before the analytes do. And the reason for that is because the solvent is there in much higher quantity than any of the analytes. So we don't want the solvent to swamp the detector. So we're going to leave the instrument off. The detector will remain unpowered until we're 1.5 minutes into the run and all of the solvent has been allowed to pass through the column. All right, and you'll also notice, as we mentioned before, that the source temperature is 200 degrees Celsius and the interface temperature is 250 degrees Celsius. Okay, so those pretty much agree with what we saw before. All right, so that takes care of that. So we've taken care of the instrument setup, and you'll want to go in and make sure that you verify those values. The next thing that we want to do is actually set up the run. So we're going to do what's called a sequence setup. So here's where we're going to define the nature of the run that we're going to do. So first of all, we want to define a sample type. So I'm going to assign this as an unknown because presumably that's what it is. And we're going to put some sort of a file name in here. Okay, so I'm going to call it, I'm going to name it after myself because I'm Jane. So I'm going to call it John 1. So it's my sample, so there you go. I'm a little vague here. All right, so the sample ID is 1. Here's the path. So basically, this is the data path. So this tells me that the data file is going to pass into the actual data storage region so we can find it later. And now we can kind of move to the side here. We also have to define an instrument method. So that's the method that we just set up. So I'm going to do a right mouse click here so that I can browse that. And I want to use the new ink because that's the instrument method that we had defined and checked before. There it is. We don't have to worry about the procedural method. The next thing is we have the auto sampler here. So I need to know the position to put the sample into. Okay, so I actually have a sample here that I want to run. Okay, so this is going to be some organic molecule dissolved in methanol as the sample. And I'm going to set it here into position 1. Okay, so you'll notice as you see here, position 1 is the third position down on the orange bar here. As you can see, I can place a large number of samples into the carousel here to run sequentially if I wish. Okay, but this will be position 1, so that's the position we're going to access. All right, the next thing I'm going to look at is the injection volume. I'm going to change that to 3 because that's exactly what we said that we'd be using in the instrument setup. Okay, if I could have left that at 10 because ultimately what's going to happen is all control of the instrument will go back to the new ink instrumentation method. All right, so I believe that's everything that I need to do to set up for the run. So I'm going to move back over to the instrument method and I'm going to hover over it here. So I'll do a a left mouse click here. Okay, so I know that I'm going to be using the correct instrument method. I want to do a single injection. So what I need to do is hover over the test tube with the arrow through it. I can do a left mouse click here. And that's going to do a single injection as opposed to a sequence injection. So that's telling me that I'm just going to run that one injection. The only thing that we have to do here is we have to make sure that our sequence set system is set to standby. And all that means is that when we get to the end of the run, we're going to turn the ion source off because I don't like the ion source to stay on. So let's go ahead and OK here. Okay, so now we get this message from the home page that basically asks us whether we want to allow the instrument to go through its sequence. And we do want it to go through the sequence, so we're going to hit yes here. Now if you go to the status menu here, you're going to notice that the auto sampler, the GC, and the MS are all basically taking instruction now from the computer. So the auto sampler is now ready to run. It's received its instructions. The GC is always the slow one, okay, because we have to make sure that the column and the injector are at the correct temperature. So it always takes a little time to do that. And then the trace MS is also ready. So if we look over at the GC here, we'll see that we have a light here that says the instrument's not ready. So as the instrument becomes ready, you'll actually see the light shift from here to ready to inject. And then you'll see a comparable message acquire over here at the status page. So at this point, we wait for a few moments until the GC decides that it's ready to go. And sometimes this may take a minute or two. So this is a good time to be patient. And we're being very patient. And I can either watch the status of the GC here on the panel, or I can watch the status of the GC over here in the status panel. Okay, so now the GC is ready and we're waiting for contact closure, which means we're waiting for injection. So now we watch the injector. So it's checking its position here. So now it's moving over to the solvent and it's now going to bring up a syringe full of solvent, as we directed it to do, to rinse the syringe. We're then going to move to the waste position. We're going to inject into the waste. Now we're going to come back to the sample again, and we're going to do our pull-ups. Okay, actually a rinse first. Back to the waste. So we've rinsed once with the methanol, we've rinsed once with the sample. Now we're going to do 2 pull-ups. There we are. And now we're going to draw some up to prepare for injection. So at this point now we're going to see the auto sampler move over to the injection position, and you'll now see the injection occur. Okay, so we've just injected 3 microliters of our sample onto the column. So at this point, you'll notice that everything is running. Auto sampler, GC, and trace MS. Now we're not going to see anything for a minute and a half because remember, we have the solvent delay happening. So again, we have to be patient. But you can again follow what's happening here on the GC. Now of course, we're also at this point going back and doing our 1 rinse post-injection. So now we're finished. So we're going to be sitting at an initial temperature of 120 degrees Celsius for the entirety of the 5-minute run because again, we're running isothermally here. Now, at this point, we're more or less going to be waiting a minute and a half because we're not going to be able to see anything happening here because again, we're not turning the detector on until we're a minute and a half into the run. However, at this point, if we want to, we can come back into home base. Okay, so I'll click there. And we want to prepare the qual browser because the qual browser is what's going to allow us to actually follow the chromatogram that we're going to be seeing. So I'm going to go ahead and go into the qual browser. And this is where we can come up and open a file. So I can say File, Open. And I'm going to a menu. And I believe I called my file John 1. So I'm going to look for that. There it is. So I can double click on John 1. And notice that I've just started the run here. So notice that I'm right at 1.5 minutes and we can see that the run has just begun and we're actually starting to generate a mass spectrum. Now at this point, if you want to follow the development of the chromatogram, we come to the keyboard and we can press the F5 key. And we notice now that every time we press the F5, we can update the top, which is the chromatogram, and the bottom is the mass spectrum. So again, we'll let this move out a little bit, and then I'll tell you a little bit about what it is that we're looking at in each one of these panels here. So again, we can continue to update with F5. We can see that something is starting to happen here. A large peak is moving through. Okay, so I'll hit F5 so we can see it. So we obviously have some sort of a component coming off the column here. So let me explain now what it is that we're looking at. The top panel here is actually called the total ion chromatogram. So what we're looking at here is the flux of ions striking the detector as our various components move through the column and off the column. So every time a new component comes off the column, we're going to see a peak. And that peak corresponds to the flux of ions that we generate when we actually ionize and fragment that component as it comes off the column. Okay? So every time you see a peak here, that's a large upflux of ions because another component has come off the column. Now, what am I looking at in the bottom panel? Well, in the bottom panel, that's going to be the mass spectrum that we're going to see as a function of where we are in the chromatogram. So for example, I can click anywhere I want on the total ion chromatogram and notice that what I'll generate down here in this panel is a mass spectrum, which is a relative abundance. So in other words, this is going to be essentially an ion count as a function of mass to charge ratio. So we can see that we have various peaks here that correspond to specific ions that I'm generating at specific mass to charge ratios. Okay, so this is basically an ion that I'm getting at about 165 AMUs. And you'll notice that I can click at different points on the total ion chromatogram, and we can see that the mass spectrum changes as various components make their way off the column here. Now all of these components, like this tiny little peak out at 1.70 minutes, that's a very minor component, but we can still see that it has a unique mass spectrum associated with it. Okay, so let's go back to F5 and update again. Okay, so we're moving right along here. We're out to 4 minutes. And so far we see that we have maybe one minor component here and one major component. Okay, and there may be a very tiny component out here just past 4 minutes. But we're going to let this finish out. And then we'll start looking at our big peak there and seeing if we can make an identification. Okay, so we'll hit F5 one more time here. And we'll know we're done because if we go back over to this point, remember as we went into standby, the source will come off, so the operate button will go dark. And at that point, of course, that means that the ion source is turned off and our run is finished. There it goes. So at this point, if I update with an F5, I'll have the total ion chromatogram across the entire run. All right, so again, if I look at my total ion chromatogram, I see that there's one major component here in the mixture, okay? So that's where I want to focus. So I want to get the mass spectrum of that component. So what I'll do is I'll hover over that peak and I'll do a left click on the mouse, and you'll notice that you're going to get a mass spectrum here. So you can see that it's a unique mass spectrum. So this is a mass spectrum that's unique to whatever the identity of that component is. So based upon the fingerprint given by the mass spectrum here, we ought to be able to make an identification of our component. Now the way to do this, if we have a nice clean mass spectrum like this, is to go up to the Actions option and click on that. At this point you can go to the library, and we're going to do a library search. So what we're doing is we're comparing our mass spectrum against a library that contains a large number of mass spectra. All right, and what it's coming up with here, and I'll go ahead and maximize this so we can see it, is this compound right here. Now what I can do is take a look at some of the statistics here. So it says our first hit, which is going to be this compound, tells me that I've got a fitting parameter match of 949. So what this essentially tells me is that I'm looking at 1,000 different fitting parameters, and it's getting 949 of them right. So what that tells me is that I have a fairly high probability of what's coming off the column being this molecule, which is benzyl alcohol. So let's take a look. I can go to name here and come across. Usually it does that for me, but another way to do it is to look down here. Here's the library spectrum that I have, and notice that it tells me that the identity of the compound from the library spectrum is benzyl alcohol. And that's what the structure is right here. So even if you can't read the name here, you can look down at the library ID and it'll tell you what it is. So this mass spectrum is our mass spectrum that we just measured, and the mass spectrum on the bottom is the library mass spectrum. And you can look at the two and see how similar that they are. As a matter of fact, you can see the residuals here. Now, you're not getting an absolutely perfect fit because, remember, among other things, we're only scanning from mass 50 up. So all of these peaks that we would expect to see down here, we're not seeing because we're basically not scanning below a mass of 50 AMUs. So that's going to account for this number not being higher than it is. All right, so that's essentially what we do. Another thing that I will show you, just so you can see how this looks, so I'm just going to X out of this and take us back, is if it turns out that you have a small peak with a lot of noise in it, you can go back to actions and do a subtract spectrum. So I can pick one range here, so I'm going to basically click down here close to the peak, maybe a little before it, generate a small range here. Now go back to my actions and do my library search. And what that does is a background subtraction, okay? And actually in this case, it ended up giving me a little bit different, and I think what I forgot to do was go back and click on the peak. So let me do that again. One range, we'll just come in here ahead. I think I just forgot to actually go back and click on the spectrum itself. So let's go back here. Get on the, there's our spectrum back again. Had to click on the peak, I forgot to do that. And now I can do my library search. And sometimes that will actually help you. In this case, it actually sent the probability down a little bit, but sometimes when you actually have a very noisy spectrum, this will actually help you. And if you actually end up looking at the residuals, it actually looks like we might have done a little better because while we have maybe a little bit more deviation here, I think there are fewer peak deviations in the total residual here. But we still essentially came out to the same compound, which is going to be the benzyl alcohol. All right, so basically to finish up, all we essentially have to do is close out, close out, close out. We don't need to save our materials here. I can go back to my instrument method and I can file, leave. That takes me out of Excalibur. And we can leave the trace tune page up, of course, which is signified by the little yellow ball down here. And other than that, we don't do anything with the instrument. The GCMS is meant to run at all times. And again, the reason for that is because every time we turn it off, it can take a day or two to pull all of the air and water back out of the system. So once it's up and running and we have a good vacuum, we like to keep it that way. Okay, this takes care of the tutorial.